Bismillahirrahmanirrahim. So we have been talking about the sinusoidal signal, the representation of analog sinusoidal signal, and we have also mentioned about the periodicity of the signal in the last class. At the end part of our last lecture, we have tried to represent our signal, analog signal, in the Cartesian plane. That means in the as a complex exponential signal. So we have shown it in the last class, and it can be shown in other way. For example, xt is an analog signal, a cos omega t plus theta, where theta is the phase, and it can be also represented as the complex conjugate of the exponential. So we have mentioned that in the last class. We can show it in the next class. So how these exponential terms can build graphically can be shown as they have made this kind of analog signal. So first of all, I would like to show the previous section first, and then we'll move to the next section, that means the complex conjugate part for understanding. Okay. So from the equation point of view, as we have already know, this xat, this a is for just to represent the analog signal, is equals to, we have the amplitude, then the sinusoidal signal cos omega t plus theta. So in this case, if we want to neglect that, okay, so the theta can be neglected because that is only the phase. Just for the simplicity, we can make it like this, where we have already mentioned that this omega is this omega. Okay, so this is another fact. So throughout this semester, we'll put capital omega and the t for the analog frequency radian per second. So this is for the radian per second, where we already know that this capital omega is equals to twice pi capital F, where F is in hertz. Okay, so we have already done this. Now our objective is to represent that this xat can also be represented as the amplitude and the phase in the complex exponential term. This is j omega t. So how that can be represented? Okay, so graphically we have done it in the last class. Just to recapitulate the things again, so let me show that. So we are representing two phases. One is the graphical representation from the real and the imaginary, and another one is this scale is for the time domain, where we are representing this is t is equals to 0, where this real axis, this axis also shows that t is equals to 0, or you can say that a phase, that means the phase is also 0. Here it is very important to understand that if we have higher omega, it has higher frequency. Okay, let me start the things. So at t is equals to 0, about this equation, so we have e to the power 0, that means the phase is 0 and the amplitude is a. We have mentioned it in the last class, just to repeat the things. So this is the value a, and what is the value in the magnitude responses? If we can plot it, so we'll find exactly the value a here. If it is moving towards the anti-clockwise direction with a frequency of omega, at a certain period of time, it will move along to the y-axis where the amplitude is still omega. But what is the perception to the real axis? What is the perception to the real axis? And we found that that is exactly 0. And find the perception is equals to 0. Similarly, if we move to the left more 90 degree, then we have the same amplitude A, and what is the perception in the real axis? So real part, the perception is, it will give the lowest maximum value. Similarly, after having a 90-degree rotation, it will be on the negative direction of the imaginary plane. And what is the perception in the magnitude response? It will give a 0 again. After having a more 90-degree, it will be on the same plane as t is equals to 0, and it will give us the perception is equals to, again, a maximum. So if we add all those points, we can find it very clearly that, so you can definitely go for in between aspects, and you will find the response to the magnitude domain. That means in the time domain, mostly in the time domain, definitely it will be a circle in the Cartesian plane. You'll find different values, and if you plot it in the magnitude response plane or in the time domain plane, you will find this kind of things. If you proceed more, definitely you will go like this, and it will continue. And as we have mentioned that this is now, this plot is exactly looks like a sinusoidal signals, what we have already mentioned. So we already established that this Cartesian plane representation is equals to this time domain representation in the sinusoidal signal. Okay, so what is the difference between if we plot this equation with omega 1 or omega 2, where omega 1 is much higher than omega 2? It mentioned that the rotational speed over there, so here how fast this vector A will rotate in the anti-clockwise, it depends on the value of omega. If omega is very faster, then it will rotate very fast, and in that case we can write that, okay, it will be faster than the changes what we have made in that case. So it will be more faster like this. I believe that you have understood the facts. So what does it mean? So here, this one, let's say omega 1 is a blue one. For the blue one, we have got this. So this is for blue one, and for the green one, so the rotation, it can be represented like the green one, omega 2, this is for omega 2. So the omega represents the frequency. Of course, there is a physical instance as well, how fast the signal will changes, how fast it will changes. And what about the A will represent the amplitude. So I believe that the whole consequences is very much clear to you. So is that clear to you, guys?
Yes, sir.
Okay. So still, yes, 69, please.
Sir, why it is necessary to represent the signal in complex exponential?
Okay.
If we need a rotating vector, we could have used the polar coordinates, right?
So I'm not sure about your question again. So you are asking, so why we should represent like this, A e to the power j omega t? That is your question?
Yes, sir.
Okay. So in future, yes, this is a very good question. And I would expect this kind of question from this class, that, so why not, why this equation? Okay, so this kind of question. Yes. To be very precise to your question, my response is that it is very easy to do the differentiation and the integration. So you can do the differentiation and the integration of a signal where it is in the form of exponential term. It's very difficult if you do the differentiations or integration if it is in the form of cos or the sine. Mostly it is very easy to understand the signal as well when it is in the time domain, where we are representing like this. That means a cos omega t, a sine omega t. It's very easy to represent in the time domain. But whenever we are moving forward from the time domain to the frequency domain, back and forth, it will be very convenient if we can plot it, or if we can represent it in the exponential term. So in future, when we talk about more about the Fourier transform, you'll see that, okay, it is very much justified. To be very precise, to do the mathematical calculation easy, to understand the mathematical calculation in an easier way, we are representing it in the exponential term. Is that fine? 69 probably.
Yes, sir.
Okay, so in future, you will get your answer more and more, inshallah, by examples. Okay. Now in the second case, now how it will also represent the same thing. That means this equation is equals to e to the power j omega t plus theta. Always neglect the theta part just for simplicity, and it can be also represented by this. Okay, so e to a by 2 e to the power j omega t plus a by 2 e to the power minus j omega t. So how it can be justified? Okay, so let me give you that graphical representation, so which will help us always in a better way. So let me write the equation first. Xat is equals to a by 2, then e to the power plus j omega t. I'm neglecting the theta, plus a by 2 e to the power minus j omega t. So I believe that if you understand these facts, it will help you in future a lot. So try to understand the things properly. And where we have already known that it is equals to a cos omega t, or we can also write a e to the power j omega t. All are the same. So how do we can present that they are same? We have already mentioned that, okay, these are the same. Now our term is how we can make it also equals to that one. Okay, so let me take the first term. Let's say p is equals to a by 2 e to the power j omega t. So I want to plot the p. So how the p looks like. Okay. So starting to the same procedure, this is the real axis and the imaginary axis. Okay, I'll plot two of those. This is for the part a by 2 e to the power j omega t, and the second part will be for a by 2 e to the power minus j omega t. So this is real axis, this is imaginary axis. So now you can help me in a way. Okay, and what about the time axis? Of course, we are plotting always the time axis. This is the amplitude and this is the time. Similar to the previous one, you can understand very easily that what is the amplitude? Now the amplitude is a by 2. Let me put it like this, half of that. So this is what? A by 2. For a by 2 at t is equals to 0, you are getting this amplitude. So at the location there, after 90 degree, a by 2. So I'm not describing all the points because we have already understood what will happen there. So a by 2, and for that one, you will get a negative maximum to some place. And when it will be this direction, it will give the 0 again. And when it will proceed to its own place again, it will give again the maximum somewhere else. Okay, let me plot it with a different color. Then we can find it very easily that, okay. And if you proceed more, definitely it will look like this. So how it looks like, definitely it looks like a cos signal. But what is the amplitude? The amplitude is what? A by 2. The amplitude is a by 2. It's also here a divided by 2. Okay. Now nothing to mention here because it is similar to the previous fact. And you know that the rotational angle or the direction is, this is omega at the anti-clockwise. Now comes to the point, another representation where we have this real, this is imaginary, and this is a by 2 e to the power minus j omega t. What does it mean by this minus?
Clockwise rotation.
Exactly. It will give you the clockwise rotation. Thank you very much for your response. And now again, with the same sort of topology, if we follow the things, you can draw it very easily. Just for understanding, I'm drawing it. I believe that you can draw that as well. A by 2. So it will again start with 0. But where now it will rotate in which direction? Definitely clockwise. After 90 degree, it will be in the direction of imaginary negative. However, the magnitude plot will give the same portion like that. So it has the impact on the magnitude is equals to 0. Okay. So after that, when it is rotating again in the clockwise 90 degree, it will give a negative maximum to some point, and when it rotates a more 90 degree to the direction, it will give again a 0 to some direction. It can come to their original position, and it will again give some point like this. And if I complete the plot in a continuous manner, so you will find a very interesting fact. Okay, if I extend more, it can be like this. What is the magnitude? Again, the magnitude is a by 2, and here is, of course, a by 2. Of course, for the for two equations or the two plots, this is omega as well as this is omega. So this shows that the frequency are the same because this is a part of the same equation. Now, if I add those two signals together, what will happen? It will give us,
Sir, overlap.
when you are adding those two together, what will be the resultant value? Definitely this a by 2 and a by 2 that will add together. So the amplitude should be a. When this is 0 and 0, that will give 0, of course. When this is a negative a by 2, that will give negative a. When you have 0 and 0, that will give again 0. When you have positive a by 2, it will give positive a. So then you can plot it like this. So you'll get exactly the same signal which we have found in case of a cos omega t or a e to the power j omega t. So if you add these two signals together, you will get back these signals what you have started with. In this way, we can prove that this xat can be represented as a by 2 e to the power j omega t plus a by 2 e to the power minus j omega t. Is that clear? Yes. First, you need to raise the hand, okay? If you want to say something. Yes. Yes, 73.
Yes, sir. Sir, so we can we also say that it is also equal to a e to the power minus j omega t?
A e to the power minus j omega t.
Yes,
Yes,
sir.
yes, you can also say that. In that case, there is a difficulties in a way. That means, what about the phase? So when we are representing, so when you are incorporating the value, okay, let me draw it here, like a cos omega t plus theta. In the convention that when we are putting this theta, where you are putting this theta, of course, this is a measurement system. You need to put it in the left side or in the right side. when you are doing that. For example, what I am meaning that when this could be written in a way that means plus theta means it is shifted to the left. Okay, so that is the convention. So that means this is leading. This is called the leading. So to represent it, you need to follow this plus j omega t plus theta convention. If you put there a negative, it will also put a negative over the theta as well. So that makes a problem. So in a convention, of course, it should be written as e to the power j omega t only, not minus j omega t. I believe the idea is clear. So this is a convention. For example, how we know that if it is e to the power j omega t, it will rotate in the anti-clockwise. This is a convention by which we are representing the fact. Similarly, if we put a cos omega t minus 120, let's say minus 120 degree, then what will happen? So it will start after 120 degree. So after 120 degree, the signal will start. So that is the convention we have set. If someone said that no, it will be plus 120 degrees, so it will definitely make some problem on your calculation. Okay, is that fine?
Yes, sir.
Okay, thank you. Okay, so I believe that you have already understood how to represent the things. In future, it will help you, inshallah, for understanding the facts more clearly. Okay. Okay, so I believe that you have done this kind of tricks in case of electrical machine as well. In case of induction motor, single phase induction motor. So if you can recall the fact that there is a like magnetic field, it is increasing in these directions, and it is decreasing and goes zero, and then increasing in the other direction. If you can recall the magnetic fields reaction in a induction motor, single phase induction motor, so you can find this kind of things. And there, this can also, these facts can also represent in a way that there are two rotating magnetic fields with the amplitude a by 2 and a by 2, and it will rotate in the anti-clockwise and the clockwise direction with the same speed of the omega, or the same speed or same frequency. And that can be represented like this. That means when the position is like this, let's say a by 2 and a by 2 at the same direction, it will give the total value is, of course, a. When in the second position, this is the value like a by 2, and this is the another one, a by 2, it will give the value is equals to 0. In the third point, if it is like this, this is a by 2 and a by 2. In that case, it is the negative of a value. So you can represent the things like this. So you have a, and it is decreasing to the 0, and then it is increasing to the negative, and again it is decreasing to the 0, which actually represent the fact we have already mentioned that this is a cause signal. Of course, the cause signal and sine signal both are known as the sinusoidal signal. Okay, so that actually been described here with this diagram. So in a single diagram, we can represent that things. That means this portion is for e to the power j omega t plus theta. Now the theta is given as a fact. So where it will start. So it will start at this point, and then it will rotate like this for a fact of theta. And for this point, e to the power minus j omega t plus theta, where it will start from there and it will rotate in the clockwise direction. So we can show it in the single diagram as well. So I have divided this diagram in two portions. and try to make you understand. Okay, so that is all about the analog signal. So what we have learned, we have talked about the analog frequency in radian, analog frequency, actual frequency in hertz, and as well as how they can be represented in linear equation, like time domain equation, A cos omega t plus theta. We have also mentioned it in the with the exponential term e to the power j omega t plus theta, and as well as how we can make a complex two terms rotating in different directions and the opposite directions. So that is a by 2 e to the power j omega t plus theta plus a by 2 e to the power minus j omega t plus theta. So up to now we have learned this. We have also talked about the periodicity of that one. So we have learned that this is the periodicity. If we represent the signal like this, x t plus tp is equals to the same as xat. So they are in the same phase after a tp period of time. So we have learned it from the analog signal. I believe that you have already the experience on the analog signal. Now we'll move to the discrete time sinusoidal signal, and we try to mention all those terms we have already learned for the analog signal. So first of all, how to represent the things. We need to always look back to our analog signal and try to match with the discrete signal as well. So analog signal was represented like this: A cos omega t plus theta. Now we are representing as A cos omega, small omega n, and then theta. As you know that, what about the discrete signal? If I draw it, actually before drawing that, we can show it here. This diagram has already drawn here. So this is the plot, of course. This is the analog signal. This is analog signal. Now we sample it. We are taking some samples. We are taking some samples. We are taking some samples. After taking the samples, so physically what happens? You have a system. This is called analog to digital converter. So let me write it like this: analog to digital converter. You are giving the analog signal. This is XAT. In the output, you are getting XN, that is the discrete signal. How the discrete signal looks like is like the same. Okay, let me take the eraser. So, okay, the signal likes the same. Like the same as this. That means you have only the stem. You have only this information. The continuous informations are not there at this moment. So you are sampling and you are getting some information. You are sampling and you are getting some information. It looks like this. You have a circuit like this. So sometimes you are adding these circuits and sometimes you are open these circuits. Whenever you are connecting these circuits, you are getting the data. And whenever you open that one, there is a missing of data. So you don't have data like there. So you don't have the data in between two samples. And to be very specific, you don't have any data. You don't have any data in between two samples. You don't have any information. So that is definitely a shortcomings of the digital or the discrete signal. Digital or the discrete signal. May I ask you one question? So if I have this kind of scenario, that means only the stems are there from the analog signal. Is that a discrete signal or digital signal? Only the stems. Yeah, 72.
Sir, it's a discrete signal.
Why not a digital signal?
Sir, if for getting digital signal, we will have to quantize the discrete signal at first. After quantization, we will get the digital signal.
Okay, very good. That means we have continuous data, and you never can say that, okay, what is the value of this second sample? You can't say that. You can say that, okay, it is between 0 to A, and it can be any data. So that's why it is still a discrete analog signal. This is a discrete, of course, this is still a analog signal. Okay, this is not a digital signal. So this is a discrete signal, of course, and this is a analog signal. This is not a digital signal. Of course, I'm happy to get this answer after having the quantization. That means after quantization, you can say that, okay, the values could be like 0, it could be 1, 2, 3, 4, and let's say A is equals to 5 volt. So 5, any value like this, whether it will be 0 or it will be 1 or it will be 2, 3, 4, 5, not in between any value, not in between any value. If you have described in between value, it can be also done like 0 and 1, you are making another point, 0.5, 1.5, 2.5, 3.5, 4.5. This is called the resolution. If you increase the resolution, yes, it can be also a discrete signal and digital signal as well. So what people try to do to make the analog signal very, very close to the digital, or digital signal very close to the analog signal. What they have done, they have increased the resolution. They have increased the resolution. Okay. So as you have seen this, we have the signal xn is equals to this. Now what we have done, we have changed this frequency. Previously it was omega, now this is omega. What is omega here? Capital omega is equals to twice pi f. This is capital omega is equals to twice pi f. Let me go back to the lecture where we have started. So here you will find that previously it was t, now this is n, where n is an integer variable called the sample number. So what is the sample number? Let me draw it here. Okay, so we have this signal like this. So here in this direction we have n. So now we have the sample number. After how many seconds we are making the sample? Let's say after del t, this is del t. After del t, not at, this is del t. After del t time, we are making the sample. So this del t, and if we make it like 1 over del t, this is our sampling frequency, fs. So fs is the sampling frequency. You can write it like this. Fs can be the time inverse of the time you are samples between two specific points, two consecutive points. So based on that, you have what is n? This is an integer variable. So it can be represented like this. This is 0, 1, 2, 3, 4, 5. It is always like this, 0, 1, 2, 3, 4, 5. Whether it gives higher frequency or lower frequency, it is always 0, 1, 2, 3, 4, 5. If it is a higher frequency, definitely the distance between 0 and 1 is very close. That is the fact. But always the number is 0, 1, 2, 3, 4, 5. So how n is related to t? How n is related to the value of t? So how we can relate those things? When the t is there, t is the time, the total time. So at the beginning, t is equals to 0, and this is at n is equals to 0. When n is equals to 1, the t is equals to what? Del t. So when n is equals to 2, then t is equals to twice del t. So you can find that we made a relation between T and N is equals as N into del T. It can be represented, isn't it? Are you with me?
Yes, sir.
Yes. For any value of N, we can write like this. Eventually, we can also we can find actual time by knowing two facts. One is N and another is del T, or in a sense, we can also write that this is N into 1 divided by Fs. By knowing this fact of the sampling frequency Fs, we can also know what is the exact time in the analog domain. Why this is important? Because whenever we are in the plane of the discrete or the digital domain, we need to come back to your analog domain in some point of time. For example, we are recording the analog signal, like my voice. This is an analog signal. It is recorded to the computer in a digital format, and then it is propagating to your computer or on your laptop or your mobile phone. And then at the end of the day, you are hearing that voice in the analog format. So you need to go back to the analog signal again. So that's why we need to have a very clear and concrete idea between the analog and the digital domain. So that's why I'm telling like this. Okay. So I believe that you understand what is the essence of the value of N. Again, the A is the amplitude, as we have done in case of analog signal. It is the amplitude of that signal. Omega is very important here because this is the frequency of the digital or discrete signal. The frequency in radians per sample. What does it mean? Per sample means you have a sample there, you have another sample. So consecutive two samples. So in between two samples, how much radian you have elapsed or you have taken. So what is the radian between these two you have elapsed? It is the representation of the frequency. I'll let you know more afterwards. And this is the theta is the phase in the radian, as we have done in case of analog signal. Now I have already mentioned that this omega is equals to twice pi f, where this f is very important. F is the cycle per sample, So how many cycles you have per sample? How many cycles you have per sample? For example, please follow this. Let me draw it. Let's say this is the full cycle. This is the full cycle, and try to take it like this. So I'm taking 1 sample, 2 sample, 3 sample, 4 sample, and 5. So actually this 5th sample. So this is 0, 1, 2, 3, and 4. And if I now erase the thing, okay, so you'll find that, okay, this is my signal. So the signal, how the signal looks like: stem, 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 and stem. So what is the cycle? So this is a full cycle. This is a full cycle. So for a full cycle, for a single cycle, how many samples you need to represent the full cycle? How many samples? Can you count it and tell me how many samples you need to represent the full cycle? Yes, 138.
Sir, 5 samples.
Yes, but as you can understand that the 5th sample, that means I need this sample number 1, 2, 3, 4. 4 is enough. The 5th sample belongs to the next cycle. The 5th sample belongs to the next cycle. For example, if I continue like this, you'll find that this sample, okay, taking like this, sample number 1, 2, 3, 4. This sample belongs to the next cycle. That's why we will neglect that sample. Okay.
Yes, sir.
So sample number, this is sample number 1, 2, 3, and 4. So we can say that the 4 sample will represent one cycle. One cycles can be represented by 4 samples. Now, so the 4 samples represents one cycles. So one sample, this is sample represents how many cycles? 1 divided by 4 cycle. Isn't it? 1 by 4 cycles. So that is called the cycles per sample. So in between 2 samples, how many cycles you have? Definitely 1 by 4, because you need 4 samples to represent the cycles. So what is the cycles per sample? So the cycles per samples is 1 by 4. And for this example, this is equals to your F, that is your frequency. That is the frequency. Now, by doing this or by understanding this, okay, let me think that this is a signal. Okay, where is that signal? It starts from here. So this is the full cycle. You'll find the full cycle is there. Okay, starting to this and to that. Okay. Can you find the value of F? Just try to count that. Okay. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Should I take the 13, number 13? No, because it is belongs to the next cycle. It is belongs to the next cycle. So we'll start with this and end with this, because this is the other one, the number 13 is belongs to the next cycle. So for a whole cycle, how many samples we need? This is number 1 and this is number 12. So how many samples we need? Total 12 samples to represent how many cycles? A single cycles.
Single cycles.
Then we can say that for a sample means between 2 samples, how many cycles it actually elapses? That is 1 by 12. And that is the value of 1 by 12 is the value for F. And that is the frequency. This is a frequency for what? The discrete domain. This is the frequency for the discrete domain. If you have any confusion, just keep it with you. Definitely it will be more clear. Okay, now we have already found that this is 1 by 12. Now, if I ask you another things, if I make it higher sampled, let me put another samples in between. The samples in between. What does it mean? Our sampling rate or sampling frequency is higher or lower? Definitely it is higher. Now, how many samples makes a cycle? How many samples makes a cycle now? Can you follow me? How many samples makes a cycle at this moment? Yes, 72.
Sir, 24.
Yes, 24 samples makes a cycle because we are doubled the sampling rate. Now, what is F? New F. It is equals to 1 divided by 24, isn't it?
Yes, sir.
Okay. Now the interesting fact is that, try to understand that. Have you changed the analog signal? Have you changed the analog signal? The answer is no. The analog signal is still like the same. The analog signal, this signal, sorry. The analog signal still belongs to the same signal. What you have changed? You have changed the sampling frequency. You have changed the sampling frequency. Previously, it was like F1, the sampling frequency, FS1, let's say, and now it is moved to FS2, where FS2 is twice time of FS1, isn't it? So you are changing the sampling frequency, and that will eventually change your discrete frequency from 1/12 to 1/24. It will change the frequency like that. It will increase the frequency or decrease the frequency. The F, it will increase or decrease. It is definitely decreased, isn't it? Whenever you are increasing the sampling frequency higher, definitely the sampling frequency, the F, will decrease. So definitely they have the relation. So we'll establish that relation. Okay, no problem. We'll establish the relation, but you can understand, you should understand that the frequency, that's why this frequency, that means cycle per sample, this is the frequency. This actually depends on two facts. One is definitely the analog frequency as well as with the sampling frequency. Since it relates with the sampling frequency, that's why this frequency is known as a relative frequency. And this omega is also relative frequency. Why? Because as we can understand, the omega is equals to what? Twice pi f. So if I have the value twice pi, what was the value? F previously, that is 1/12. So from there you can find what is the value of omega. That was nothing but pi/6. Now after having the change, you will find omega is equals to twice pi 1/24. After changing the sampling frequency, now omega is equals to pi divided by 12. So this omega and this f, to my understanding, it's very easy to understand the value of f physically. You can understand, you can count the points, and from there you can find, okay, how many samples makes a cycle, and from there you can find physically what is the value of small f, and this small f is nothing but cycle per sample, and it is, both of those are relative frequency. Why they are relative frequency? Why they are relative? Because they are relative to the sampling frequency. Even though the analog signal remains the same, but the frequency can be changed. I'm asking very lame question. In analog signal, if the frequency is 1 hertz, can you change that frequency? If my voice signal is 1 hertz, let's say there is a sound like key, like that, okay? If that is like 20 kilohertz, a signal is 20 kilohertz, it will remain 20 kilohertz. You can't change that. But if that is even 20 kilohertz, you can make it the discrete or digital, then you can change the frequency in the discrete domain because it is a relative frequency. It is a relative frequency. If I plot it in the frequency domain, let me give you one example. Now I'm plotting it in the frequency domain, in the discrete frequency domain, where this is the like xf magnitude, okay, magnitude of the signal. What I am doing, this was the analog signal, the red line. This is given, passing it through the analog to digital converter, and in the output we are getting what? Xn. How the Xn looks like? Xn looks like this. Okay, if I erase this red line, this is your Xn. Now I'm talking about what is the frequency of this Xn in the discrete domain, and that is the small f. So let's say, where is the small f? What is the value? We have already found that this is 1/12. So where is that? Okay, let me draw it here. Okay, so this is the point. This is what? This is 1/12. Let me do that. And what is the strength of this signal? Let's say this is the strength of the signal. Okay. don't think about this. What is the strength at this moment? So it is like that. Now, if I double the sampling frequency, I have already mentioned that, double the sampling frequency. So it was previously like del t was 2 seconds. Now del t is equals to 1 second. When it was 2 seconds, it was 1 by del t, and now this is 1 by del t. So previously it was like this, what, 2s, 1 by 2s is 0.5. Now this is 1. So the sampling frequency eventually increased by double, 2 times. So sampling frequency increased. So you have more samples in between. Okay, so I have already mentioned. And now where is the sampling frequency? Where is the frequency? F. Now, this is the F scale. It is converted from 1 by 12 to 1 by 24. Is that increased or decreased? It is decreased.
Decreased.
Yeah, decreased by twice time. So now the thing is like this. So this is the point, 1 by 24. However, you have the same analog signal. Can you increase or decrease this discrete signal? Can you, by fixing the analog signal, by taking a single analog signal, let's say this analog signal frequency is 2 kilohertz. By this 2 kilohertz, can you change the discrete frequency or digital frequency? Yes or no? Can you change?
Yes, sir.
Yes, you can. So how you can change that? By changing what?
By changing the sampling frequency.
Exactly. By changing the sampling frequency. So is that related to some term? Is this frequency related to some term? Yes or no?
Yes, sir.
Yes, to the sampling frequency. So that's why this is known as relative frequency. This is not the actual frequency. What is the actual frequency? The actual frequency is like 2 kilohertz. In several questions or in several vivas, people can ask you that why this is called relative frequency and why this frequency is a little bit different than the analog frequency. Okay, now may I ask you another question to the same point? Let's say we have the F. Now we have the F is equals to 1 divided by 24. 1 divided by 24. So what is the story? The storyline is that you have a 2 kilohertz signal. You have sampled in a way so that 24 samples makes a cycle. From there, you have found that F is equals to 1 by 24, and you have drawn like this. Okay. Now, if I change this analog signal as 4 kilohertz, then for the same situation, what would be the value of F?
Sir, 1 by 12.
So any other answer? 34.
Sir, it will remain the same because the spectrum doesn't vary the kind of the frequency.
So one of your friends told that F could be like 1 by 24. This is the second answer from 34, and one of your friends tell that it would be 1 by 12. Okay. Any other possibilities? Okay. So let me give you this answer with the graphical representation so that you can justify your own answer. So first of all, I have the signal. Let's say take it like 2 kilohertz. Okay, so just take that. This is the full cycle. This is the, okay, let me take a sinusoidal, so it will help me to draw the things and to understand. So we have, let's say, how many samples? Give me the quick response. So let's say this is 2 kilohertz. Okay. And now how many samples you need to represent the whole cycle? How many samples? How many samples you need?
Sir, 4, sir.
4 samples. 4 is cycle. So it is f is equals to 1/4. Very easy. Now what we are telling, so we can plot it. We can plot it in the frequency domain. And let's say this is that 1 divided by 4, or eventually 0.25. Now what we are doing, we are increasing this analog frequency with the same situation. So we are increasing the analog frequency with the same situation. Increasing means now 4 kilohertz. So how can I plot it? Okay. I believe I have done the correct things. And now, where are the samples? Samples remaining the same points. They will hold the same points. This point, this point, this point, because you have not changed the sampling frequency. Now, how many? So now can you tell me what is the value of f?
Sir, half.
How many samples you need to represent the whole cycle?
Sir, 2 samples.
2 samples per a cycle. So definitely it is now half of that. Half means 0.5. And this is very logical. Why not? Because when the analog signal frequency will increase, definitely there would be some impact to the digital domain as well, isn't it? So one of our friend already mentioned that if it was like 1/24 before, after having double of the analog frequency, it will be like 1/12. That is the correct answer. And you can justify yourself with this graphical representation. So number 1, how the discrete frequency could be changed if the analog signal will remain constant. How the discrete signal could be changed if the analog signal remain constant. I'm expecting answer.
By changing the sampling frequency.
Exactly. So by changing the sampling frequency, in this case, analog signal remain constant. Analog signal, this is constant. Number 2, how the relative frequency would be changed if the fs remain constant.
Sir, by changing the analog signal frequency.
By changing the analog signal frequency. So we can conclude that this discrete frequency or relative frequency actually can be changed by the sampling frequency as well as by changing the analog signal frequency, both. And never try to memorize the things, try to understand the things by the graphical representation. That will definitely help you at the long run. So whatever, so in the throughout this session or throughout this course, we will take the analog signal. We have a constant sampling frequency. So we'll take our sampling frequency constant for a whole circuit. So there are some concept. There's a multi-rate signal processing. It's called multi-rate signal processing because in that case, a part of the circuit has a different kind of sampling frequency. So it is a bit complex in a way, but at this moment for the digital signal processing 1, we will consider that for the whole circuit, whenever we are taking that fs is equals to, let's say, 20 kilohertz, it will remain 20 kilohertz for the whole example. Okay, so that makes our life easy. So that means, so the sampling frequency will remain constant, though we have already described how the discrete frequency is related to our sampling frequency. Okay, so that is the end of today's session. So we we'll continue this session, or we'll continue these examples. That means the digital example. So today we have learned about the discrete signal, and from the next day we'll talk about a few characteristics of the discrete signal, inshallah. Thank you for your participations.